magnetic dipole moment of a revolving electron. Have a nucleus, we will have an electron, single proton, single electron, and these two will be at a distance. Let us say this distance is r, and there is an electron with a charge of E minus, and this is going to be Ze plus, and because it is hydrogen atom, that Z is going to become 1. When the electron, let us say the electron is revolving like this, it is going to produce a magnetic field which is going to be, if I say this is the charge, the magnetic field is going to be something like this. It is going into the plane of the board, that is going to come out from the center of the nucleus. So that's how the magnetic field is going to be produced. Equals Q divided by T. So we have a charge, that is the charge of electron. It is in motion, it is going to revolve around the nucleus, and for that revolution, it is going to take some time. So I can replace this Q by this E, and this T, which is a random time, with a capital letter T, because this electron is going to revolve with a fixed time period. If I want the time period, I want the value of this time period, T equals, if it is distance by time, if I want the time, it will be rearranged, it will be like this, V is equal to distance by time. If I want time, it will be distance by velocity. So if I want the time here, it will be the distance traveled. How much distance it is going to travel? It is going to be one revolution, and one revolution will be the circumference of this circle, that is the circumference of that orbit. So it will be 2 pi divided by the velocity, let us say the velocity is V. So that is the time period. Now I can substitute this term for this time period into this equation. So I equation becomes I is equal to E divided by 2 pi R divided by V. Now because this is a multi-layered fraction, this E can come up, so it is going to become EV, that equation. So this is EV divided by 2 pi R, and this is what? This is the expression for current equals I into A. That is the equation for the magnetic dipole moment will be replaced by mu, and that mu will be again I into A. Now this mu, it represents a microscopic magnetic dipole moment. If I take it as mu 1, I am talking of the first orbital. If I take it as mu 2, I am talking of the second orbital. Likewise, I can apply that mu for any of the orbit or any of the electron in any of the orbit in any of the atom. So what I want to have here is this mu term, which is the product of I and A. I have the equation for I, but I need the equation for A. Now what is A? A is the area of the circle which is produced by this radius of this orbit. So this A can be written as pi r. So if I take this and write the equation for mu, that mu is going to become I into A equals, I is this thing, EV divided by 2 pi r multiplied by A is going to be pi r square. So that is the equation. Now I have r in the denominator, r square in the numerator, one of the r cancels out, the pi goes out, what is left is EV, there is a single r left in the numerator, and divided by 2. So my equation for mu, it is going to be EV r divided by 2. L equals mv. L is also equal to, because of the Bohr's orbit, it will be nh by 2 pi. So in the beginning, what we want here is, for now, for the next step, I want this mvr to be present in the numerator. Now, if I want that, what I need to do, I need to multiply and divide by m, and this will be me, that is the mass of electron. So I will just rearrange the same equation. So mu, it is going to become mu equals to E into MEVR, that is the, now this bracket term can be replaced by this L. In the denominator, it will be only 2me. Now I can replace that MVR by this L, that is the angular momentum. So mu can be written as E divided by 2me into L. So this is the expression of the dipole moment of an electron in the orbit in terms of the angular momentum of the electron. Now what I am going to do here is mu divided by L. These two are the unknown quantities in this equation. Mu is unknown, L is unknown, but E, that is the charge of electron, is known, and me, that is the mass of electron, that is also a known quantity. Mu divided by L, it is going to become E divided by 2me. Now right hand side is the known quantities. I can substitute those values, and that is going to become 1.6 into 10 to the power minus 19 divided by 2 into mass of electron is 9.1 into 10 to the power of minus 31. Mu by L equals to 8.8 into 10 to the power of 10. And because on the right hand side we have the charge by mass, it is going to be coulomb per kg. So I hope if you are trying this calculation, you should get the same value. And this value is called as gyromagnetic ratio. Gyromagnetic ratio. I'm continuing with the same step again, going back. So it will be mu equals to E divided by 2 me into L. I just write it down separately. I can use this equation that is from the Bohr's second postulate that can be substituted here in the place of L. So what I'm going to get here is mu is equal to E divided by 2 me into nh divided by 2 pi. Now I have the general equation for the magnetic dipole moment of an electron in the orbit. Take it as mu1, that means n is going to be taken as 1. So the value of n is going to be taken as 1 and we are going to talk about the first orbital of that electron and we are going to write a subscript for mu as 1. This will be equal to, I have n is 1, I'm going to drop that, E is 1.6 into 10 to the power of minus 19 into h is the Planck's constant, that is going to be 6.636 into 10 to the power of minus 34 divided by 2 into 2, I can take it as 4. Me is the mass of electron, 9.1 into 10 to the power of minus 31 into what I have is pi is 3.14. So I have substituted all the constants. Now if I simplify all these numbers, I am going to get the value of this mu, get this number 9.27 into 10 to the power of minus 24. And dipole moment will be ampere meter square. And this value is the result of this derivation, that is the magnetic dipole moment of revolving electron, and the value here it represents for the first orbital of the electron in the hydrogen atom, and this value has got a special name, and everything, because everything is mostly done by Niels Bohr, this value is called as Bohr magneton.